This is Dr. Shankaraiah from Department of Physics. Today I am going to discuss numerical problems on superconducting material. So this is module 4, which is magnetic and superconducting materials. So in module 4 we are discussing numerical problems on superconductivity. So this is the topic of today's presentation. So the first numerical problem is that the transition temperature for lead is to 7.2 Kelvin. However, at 5 Kelvin, it loses the superconducting property if subjected to magnetic field of 3.3 into 10 power 4 amperes per meter. Okay, so this lead superconductor is going to lose its superconducting property if subjected to magnetic field of this 3.3 into 10 power 4 ampere per meter at 5 Kelvin temperatures. So find the maximum value of H which will allow the metal to retain its superconductivity at 0 Kelvin. So we are going to find the maximum value of the magnetic field H. Okay, so that this material lead is going to retain its superconducting property at 0 Kelvin. Okay, so we have to calculate the H maximum value of H. Maximum value of H, X maximum, where the material will still retain its superconducting state. So first we have to start with the given. Whatever inputs are given, we have to mention those inputs, right? So they have given the transition temperature for lead is 7.2 Kelvin. So the transition temperature is Tc. Tc is given as 7.2 Kelvin. And then critical field. Okay, critical field is given as 3.3 into 10 power 4 amperes per meter. Why are we saying this as critical field Hc of T? Because they mentioned that at 5 Kelvin, it loses the superconducting property if subjected to a magnetic field of 3.3. So the material is in superconducting state at 5 Kelvin. This material lead is going to lose its superconducting property if we apply this magnetic field. So, okay. So when H is greater than Hc, greater than or equal to Hc, the superconducting state is going to change into a normal state. So that is why this is the critical magnetic field Hc of T. And then they have mentioned the other temperature 5 Kelvin. 5 Kelvin is the temperature where it is going to lose its superconducting state if we apply this critical magnetic field 3.3 into 10 power 4 amperes per meter. Okay. So now we have to calculate the maximum value of H, at which will allow the metal to retain its superconducting state at 0 Kelvin. Okay. So we know the equation for this critical field Hc of T is equal to Hc of 0 into 1 minus T by Tc whole square. So this is the equation which we can use to calculate the critical magnetic field and the field at 0 Kelvin. This 0 is nothing but T is equal to 0. Okay. So this is T is equal to 0. So Hc of 0 is the critical field at a temperature T is equal to 0. Okay. So using this equation, we can calculate various parameters. We can calculate critical field Hc at any temperature T. We can calculate critical field at 0 temperature, and we can also calculate T and Tc. Right. So in this problem, they have asked us to calculate the maximum value of H at 0 Kelvin. So we need to find out this Hc of 0. At 0 Kelvin, what is the field, critical field? Okay, so which we can apply so that this lead material is going to retain its superconducting state. Okay, so that is why we have rewritten this equation as Hc. We need Hc of 0. So Hc of 0 is equal to Hc of T divided by this whole bracket 1 minus T square by Tc square. Okay, so that is what we got here, Hc of 0. So this 0 means at T is equal to 0. What is the critical field? What is the maximum value of field which we can apply so that the material retain its superconducting state? Okay, so this is Hc of 0 is equal to Hc of D by 1 minus T square by Tc square. Okay. So we know what is the value of Hc of T. Hc of T is given. Right, substitute the value of Hc of T, which is 3.3 into 10 power 4, then 1 minus T square. T is 5. T is 5 Kelvin, so T square is 25. divided by Tc square. Tc square is 7.2 whole square, that is 51.84. Okay. So now we can calculate this. Then we are going to end up the value of 6.37 into 10 power 4 amperes per meter. So this is the critical field that we can apply to this material at 0 Kelvin temperature, so that the material will still remain in superconducting state. Okay. So yeah. So this is the equation which we have used to find out the critical field at 0 at T is equal to 0. Using this equation, we can find out various parameters. Okay, by rewriting this equation, we can find out Tc also. By directly, we can also find out the critical field at any temperature T, at any finite temperature T. So this is the first numerical problem. The second one is the critical field of niobium is 1.5 into 10 power 1 into 10 power 4 10 power 5 sorry 10 power 5 amperes per meter at 8 Kelvin. So this is the temperature, and 2 into 10 power 4 or 10 power 5 amperes per meter at 0 Kelvin. Okay. So they have given the critical field, Hc of T is given. Critical field is 10 power 5 amperes per meter. Hc of T is given as 10 power 5 amperes per meter and at a temperature of 8 Kelvin. And the critical field, this is at 8 Kelvin, and another Hc of T, so this is Hc of 1, Hc2 is given as 2 into 10 power 5 ampere per meter at 0 Kelvin. Okay. So calculate the transition temperature of the element. We have to calculate the transition temperature Tc. So what is the critical temperature for this material which is having these critical fields at these temperatures? Okay. So always start with given. So they have given Hc of T, which is 1 into 10 power 5 amperes per meter, and temperature is given as 8 Kelvin. Hc of 0. Okay, so at 0 Kelvin the critical field is 2 into 10 power 5 ampere per meter. So Hc of 0 is also given, and we need to find out this transition temperature Tc. Okay, so again we are going to use the same formula, right? So same formula, so that is Hc of T. Whatever we have used in the first numerical problem, in solving the numerical problem 1, Hc of T is equal to Hc of 0 into 1 minus T square by Tc square. Okay. So using this equation, we can calculate Tc square or Tc, right? So we need to rewrite this equation. We need Tc square. So first let us rewrite this equation. So Hc of T divided by Hc of 0 is equal to 1 minus T square by Tc square. Okay. So yeah, so from this equation we need Tc. So T square by Tc square is equal to 1 plus Hc of T divided by Hc of 0. Okay. Yeah. So let me rewrite here. Okay. So T square by Tc square is equal to 1 plus, yeah, so yeah, this is, we need Tc, so that will be this, so this will be minus, sorry, this will be minus, right? So because T in front of T square by Tc square there is a minus sign, so we want positive value, so Hc of this term will go that side, so 1 minus Hc of T divided by Hc of 0. Okay. So again we want Tc square, so T square by, let us take this side, 1 minus Hc of T divided by Hc of 0 is equal to Tc square. Okay. So Tc will be square root or whole power of this. Okay. What will be, so this is Tc square. So if you want to write Tc, so that will be T, because square will go T divided by 1 minus Hc of T divided by Hc of 0 whole power of. So that is what I have the equation here. This is the equation I already have. So I just derived how we got this equation from the equation of the critical field. Hc of T is equal to Hc of 0 into 1 minus T square by Tc square. Okay. From this equation, we finally got this equation Tc is equal to T divided by 1 minus Hc of T by Hc of 0 whole power 1 by 2. Okay. So yeah. So now they have given T. T is 8 Kelvin. Substitute the value of T and Hc of T. Hc of T also is given. Hc of T is given 10 power 5 ampere per meter. Okay. And then Hc of 0 is 2 into 10 power 5. So substituting all these values, we got around 11.3 Kelvin is the critical temperature. So Tc for this niobium is 11.3 Kelvin. So above T for T greater than Tc, it is going to lose its superconducting state and it will be changing into normal state. Yeah. So we have calculated the transition temperature or critical temperature for this niobium element. Okay. So let us go into the third numerical problem. Okay, so third numerical problem is that the critical magnetic field at 5 Kelvin is 2 into 10 power 3 ampere per meter in a superconductor ring of radius 0.02 meters. So critical magnetic field is given. Okay, so critical magnetic field Hc of T is given, that is 10 power 3, 2 into 10 power 3 ampere per meter, and at a temperature of 5 Kelvin. Okay. Now, and superconducting ring as a radius is also given. Radius is around 0.02 meters. Find the value of critical current. So we need to calculate the value of critical current. What is the critical current IC? We need to find out this IC. Okay. So I will start with given. They have given the critical field is 2 into 10 power 3 ampere per meter. Temperature is given as 5 Kelvin. Radius is given as 0.02 meters. Using this equation of current, so this is the equation of current. IC is equal to 2 pi R into HC, where R is the radius. R is the radius. Okay. So 2 pi is pi value, we have to take it 3.143, and R is given as 0.02 meters and HC is also given as 2 into 10 power 3. Substituting all these values, we are going to get the critical current. Okay. So the critical current is around 251.4 amperes. Okay. So yeah. So given the critical magnetic field and temperature and radius of a superconducting ring, here we have calculated the critical current. Okay. So we know that the material is going to lose its superconducting state for I greater than IC. And for I greater than IC, the material will be in normal state, and I less than IC, the material will be in superconducting state. Okay. So yeah. So this IC is the critical current. So based on the critical current also, the material can be in either in superconducting state or in normal state. Going into the fourth problem. So the fourth numerical problem is that a superconducting tin has critical temperature of 3.7 at 0 magnetic field, and critical field is around 0.0306 amperes per meter at 0 Kelvin. Okay. So first they have given superconducting tin as critical temperature Tc is given at 0 magnetic field. Okay. So Hc of 0, and critical field Hc of T is given at 0 Kelvin. Yeah. So Hc of 0, that means at 0 Kelvin, what is the critical field? That is also given. Now find the critical field at 2 Kelvin. Hc of T we need to calculate. And then once we calculate the critical field, we also need to calculate current IC. What is the current? These two parameters we need to calculate. So they have given, I will start with given. So given critical temperature is 3.7 Kelvin, transition temperature. Critical field at 0 Kelvin is 0.0306. So that is Hc of 0, right? So this is actually Hc of 0. And the radius of the superconducting ring is given as 1 meters. And now using this equation, this same equation which we have discussed, right, in the first problem and second problem also, we have used the same equation. Hc of T is equal to Hc of 0 into 1 minus T square by Tc square. Using this equation, we are going to find out the critical field Hc. Okay, so Hc of 0 is given as 0.0306 and 1 minus T square. T square is given. T square temperature is around 2 Kelvin. Okay, T is given as 2. So T square is 4 and Tc square. Tc is given as 3.7. So square that out. So by substituting all the values of H0, T and Tc, we are going to get the critical field Hc, which is around 0.02166 amperes per meter. Once we get this critical field, they also asked us to calculate the critical current. Okay, so the critical current equation is this: IC is equal to 2 pi R into Hc. Okay, so this is the equation for critical current, where R is radius. So they have given radius as 1 meter, right? So substitute all the values here. 2 pi R is given as 1, and Hc we have calculated 0.021 is 166 amperes per meter. So substituting all the values in this equation for current, we are going to calculate the critical current, which is 0.136 amperes. Okay, so we have calculated the critical magnetic field at 2 Kelvin. Also, we have calculated the critical current. Okay, so critical current for T greater than IC, I greater than IC, the material is going to change its superconducting state into a normal state. So yeah, so for H greater than Hc, material will go into a normal state from superconducting state. The material will go from superconducting state to normal state, and for I greater than IC also, material will go from superconducting state to normal state. So for this material given, we have calculated the critical magnetic field as well as critical current. Okay. So let us go into the next problem. Calculate the critical current for a wire of lead having a diameter of 1 millimeter at 4.2 Kelvin. Okay. So we need to calculate the critical current IC for this problem. We need to calculate this critical current. Given lead is the material having diameter is given now. So diameter is given. We need to calculate radius. So diameter is given as 1 millimeter. So from this we need to calculate radius and a temperature of 4.2 Kelvin. So the critical temperature for lead is 7.818 Kelvin and critical field at 0 Kelvin is given. So critical field at 0 Kelvin is given as 6.5 into 10 power 4 amperes per meter, and critical temperature is also given as 7.18 Kelvin. So yeah, then diameter is 1 millimeter. So convert this into meters. Okay, or yeah, so we can, yeah, so 1 millimeter is diameter, so the radius will be 0.5 millimeters, right? Yeah, and then millimeters have to be converted into meters, so 0.5 into 10 power 5 minus 3 meters. Okay, first we need to calculate critical magnetic field to calculate critical current, because in the equation of critical current, IC is equal to 2 pi R into Hc, where Hc is the critical field. So they have not given critical field, so we need to calculate critical field using this equation. Hc is equal to H0 into 1 minus T square by Tc square. Okay, using this equation, we can calculate Hc, critical field, then we can substitute this Hc in the equation for current. Okay. So H0 is given, the critical field at a absolute 0 Kelvin, 0 temperature, 6.5 into 10 power 4, substitute the value of H0, 1 minus T is given as, so T is given as 4.2 Kelvin, so we need to write temperature T is given as 4.2 Kelvin, so substitute the value of T, and Tc is given as 7.18 Kelvin, so that is critical temperature is 7.18 Kelvin. Substituting all these values, we are going to find out the critical field, which is 42.758 into 10 power 3 amperes per meter. Then once we find out this critical magnetic field, we are going to substitute this critical magnetic field in the equation for critical current. So IC is equal to 2 pi R into Hc. So radius is given, diameter is given actually. So from diameter we have calculated radius, and Hc also, the critical field also we have calculated. So substitute all the values in this equation for current. 2 pi value 3.143, R value is 0.5 into 10 power minus 3 converted into meters, and Hc is the critical magnetic field, which is 42.758. okay, into 10 power 3 amperes per meter. So substituting all the values, we find out that the critical current for this material is around 134.26 amperes. Okay. So for I greater than IC, for current greater than this 134.26 amperes, the material lead will go from superconducting state to normal state. So here we have calculated the critical current. To calculate the critical current, we have first calculated the critical magnetic field, and then we have used this equation to find out the critical. So these are the some of the reference books which I have used in making up the presentation. And to summarize, we have solved some numerical problems. So basically in this presentation, I have solved numerical problems on superconducting materials, on superconductors. Okay. So we have solved some numerical problems on superconductors where we have used equations. So basically we have used the equation of critical magnetic field Hc of t equal to Hc naught or Hc of 0 into 1 minus t square by Tc square. So using this equation, we can rewrite this equation to find out various parameters. For example, directly we can calculate the critical field Hc of t from this equation given Hc of 0, t and Tc, or we can find out Hc of 0, the critical field at 0 Kelvin, by rewriting this equation. Hc of 0 is equal to Hc of d divided by this whole square bracket. Then we can calculate Hc naught. Similarly, we can rewrite this equation to calculate Tc, critical temperature, right? So this equation can be used to calculate various parameters. Also, we have calculated the critical current using this equation, where R is the radius of the superconducting ring and Hc is the critical magnetic field, and value of I is 3.143. Okay, so these are the two equations we have used to calculate various parameters of critical magnetic field at any finite t and critical field at absolute 0 Kelvin, and to find out the transition temperature and to find out the critical current. So yeah, so in this presentation we basically solve the numerical problems, and in the next presentation, so with this we have completed module 4, and in the next presentation we will start another module which is nanotechnology. The fifth module is nanotechnology. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.